Let's talk now about the idea of greedy algorithms. So many types of problems can be classified as optimization problems. That is, we want to minimize or maximize something in order to get the best solution. Okay, so maybe we want to minimize cost, minimize our time spent on something, maximize our profit, something like that. So how do we go about solving optimization problems? Well, there's lots of different ways to try to solve them, and specific problems have different solution methods. But one way of approaching optimization problems is to use what's called greedy algorithms. So what's the basic idea behind greedy algorithms? So we'll have a series of decisions or a series of decision points. And the idea of a greedy algorithm is that at each decision point, we choose the best option. We're going to put it in quotes. Best option at that point. I put it in quotes because for any of these, you have to decide what you consider best. All right? Now, one of the things to consider when you're using greedy approaches is that sometimes they produce the overall or global solution, but sometimes they don't. At step 2 here, when we're choosing the best, we're choosing what we would consider a locally optimal solution. Okay? So as far as number 3 is concerned, once again, it depends on the type of problem. There are some types of problems for which algorithms are known that use a greedy approach, and they're still guaranteed to get a global solution. But there's other types of problems for which we don't necessarily know how to find the optimal solution. Right? Or at least not necessarily with a greedy approach. So why not just make the overall best decisions? Well, we may not be able to. Okay? One problem. Let's say I had a function. I don't know what the actual function would be, but let's say it has x1, x2, x3, x10 as input values. Well, depending on the function, there may be no known way of figuring out what the optimal solution to the function is, whether it's minimizing or maximizing. If these values come from the set of real numbers, there could be an infinite number of combinations that I could plug in here, and it may be the only way to determine the absolute optimal solution is to try every possibility. Well, if there's infinite possibilities, that's obviously not something I can do. Even when we have a finite number of options, it may not be computationally feasible. So number 2 here, we'll say even with a finite number of combinations, it may not be computationally feasible. What do I mean by that? Well, maybe given the algorithms for solving this problem that we currently know about, and given the computational performance of current computers, maybe it takes 100 years to check all the possibilities. Well, nobody has 100 years to wait, so that's not really a possibility. Another potential problem is that it could be that in order to find the optimal solution, you'd have to know about everything in advance. If we go back to our series of decision points, maybe you have to have all the data first and then go through and see what to do. Well, there's some problems that's not a possibility. I mean, think about driving, for example. Anybody who's driven any real length of time has probably been stuck in a traffic jam. Now, while you can know in advance about some traffic jams, there's other traffic jams you don't basically know about until you get there. And so you could plan the shortest time to get from point A to point B if you knew about every road condition before you ever left your house, but that's not really feasible, right? So, may not have all information at decision time. Okay? So let's look at a couple simple examples of how greedy algorithms might work. So let's say for this problem, we have point A, here's point B, this is say 50 miles. This is point C. We'll say this is 45 miles, 30 miles between them. Here's point D, this is 10 miles. And if we come around here, maybe that's 42 miles. So let's say starting at A, we want to visit each of the 4 places, or the 3 additional places, maybe more than once, but we want to do such that we minimize our overall distance. So if I'm using a greedy approach, I might say, well, I could go from A to B, and this is a cost of 50, but going from A to C, that's only a cost of 45, so I'm going to choose that. So see, I have AC, and then when I get here, maybe I go to D. And if I were to go to D to B, then our overall distance would be 45 plus 10 plus 42, which is what? 55, that'd be 97. Okay? You might look and say, well, what if I did this? I go from A to C to D, back to C to B. Okay, so that's 45 plus 10 plus another 10 plus 30 is equal to 45, 55, 65. That's 95, so yeah, it is actually a little better. But what if I went to B first? A to B to C to D. So that's 50 plus 30 plus 10 is 90. And we could also go from B to D back to C, but that's going to be longer. But this one's better, and I think it probably is the overall best solution. But I don't get that if I choose the shortest route when I leave. Okay? So here I'm using the greedy approach of picking the smallest of my options at each step, but that doesn't lead to the best overall solution. All right? So there's one example. Another example is something called a knapsack problem. And the idea behind this, the general story that you would be given as an example of knapsack problem would be where you have a burglar who breaks into a place, and he has a knapsack that he can put items in that he's going to steal. And so he would like to leave with the most value in his knapsack. Okay? But let's say his knapsack, for the sake of keeping this simple, let's say his knapsack can store 6 pounds of items total. 6 pounds of, items. And I'm going to draw it like a physical shape. Okay? And he has several items to choose from. Now, the items that we put in the knapsack will all have 2 properties. One will be, like in this case, a weight. It's 1 pounds. And the second thing will be a value, which here we'll say dollars. So, in terms of practical applications, it doesn't really have to be pounds. I could have used physical dimensions, which might make more sense for a knapsack, like maybe it's 6 square units. or something like that, where it's a quote unquote size, right, in weight or physical dimensions or whatever, and then a value. So let's say the items in order are something weighs 5 pounds and it's worth $10, something weighs 4 pounds and it's worth $7, and something else weighs 2 pounds and it's worth $4. Well, if he's looking at which one's worth the most, and you could even, there's other approaches to this, it might look at value per, say, pound. So this would be, 10 divided by 5 equals $2 per pound. This would be 7/4 dollars per pound, which is under 2. And this would also be 4 divided by 2 equals $2 per pound. If he goes with the one that seems the biggest here, 5, well, that's eating up this space right here, so he gets $10 for this. But if instead he had skipped the $5 and put in the 4-pound one and the 2-pound one, he could have filled his entire bag and got 7 plus 4 equals $11. Sorry, 11. So he could have gotten more value by skipping the biggest item here. Okay? So there are solutions to solving the knapsack problem, but for this type of this version of it, there's different versions of it, but for this version, greedy approaches aren't guaranteed to get an optimal solution like we saw here. It wasn't guaranteed. All right? If we allow fractional amounts, like if these have been, bags of gold dust or something like that, where you could fill it all up and use a partial one, then greedy can lead to an optimal solution. But here it's sort of take all this or take all this or take all this. All right? Now, what if we'd had a 1-pound item, say worth $1 or say $2? Well, then the greedy approach would have led to an optimal solution, because I would have used the 5 and then I would have used the 1 right here and gotten, say, $12. Okay? So it is possible, but it's not guaranteed here. But that's using the greedy approach, and there are a number of different types of problems in data structures or algorithms that use greedy approaches. Graphs, a lot of the graph algorithms use greedy approaches, but there's other types of problems in addition to the ones I showed you. But that's the basic idea.